Hi everyone, welcome to the second interference video. So this is just the second part of interference. The first part was looking at when you had like two speakers or two light sources that were coherent, and looking at the path difference and seeing how interference patterns were created with that. This is interference patterns made by using a grating. Now, first things first, I want to talk about what a grating actually is. Usually, obviously in class I would show you what a grating is, but I can't do that. So a grating is just a bit of like glass with a lot of little grooves in it. Okay, so you can think of it as like metal bars or something like that. Um, and what that does is the light comes through one side and then obviously the light can only travel through these wee slits. Okay, this is what they actually look like. You can't really even see the little slits in them at all because they're so small. Hopefully you can see what these say. This one says 100 lines per millimeter, this one says 300 lines per millimeter, and this one says 600 lines per millimeter. So that just gives you an idea about how many of these little slits that the gratings actually have. Okay, so 600 little lines per millimeter is a lot. Okay, so that's what a grating is. So as I said, a grating is a slide that consists of many equally spaced slits positioned extremely close together. Light is diffracted as it passes through each slit, and this causes interference to take place. Okay, so usually what I'd do is I would get a laser and show you what happens when we put laser light through a grating. Unfortunately, we can't do that, but I will show you some diagrams. Now, this diagram, it's not the easiest to follow, but hopefully I'll obviously explain and hopefully that'll make sense. So first things first, I just want you to remember what diffraction is. Okay, diffraction is when light or sound goes through a small gap and spreads out from that gap. Okay, so that's diffraction. So if we had laser light and it went through two slits, obviously our gratings have thousands of slits on them, okay, but let's just say two slits here. Okay, that means that the laser light is being diffracted out of this slit, but also diffracted out of this slit like that. Okay, and when those two sources diffract, their wave fronts meet up crest to crest, trough to trough. Okay, so you can see that these two waves here are meeting crest to crest, okay, or trough to trough, and we get destructive or constructive interference. Okay, this is what we'd actually see if we did this experiment. So if I put through red laser light through a diffraction grating, what we'd see is something like this. Okay, so we'd see points of constructive interference, points of destructive interference, points of constructive interference, points of destructive interference, constructive, destructive. Okay, and it depends on a few things as to whether we see something like this or something like this. So the points of maximum obviously being further away from each other in this one than the points of maximum here. So that's if we shine through a laser of a monochromatic source. If we put through a white light source, we'd see something like this, and we'll talk about this a little bit later on. A white light source will come through and our central maximum will just be white light. But then our other maximums here, our other points of constructive interference, will actually be little spectra. Okay, and we'll talk about that a little bit later on and talk about what type of questions you can be asked to do with that. So when we use a grating, there are a few different things we can do to increase the distance between the maxima. Okay, increasing the number of slits in the grating increases the distance between the maxima. It just means that the maxima or the points of constructive interference will be further away from each other. Increasing the distance to the screen. So what I mean by that is if we were doing this experiment in class and I had the grating and I was holding it up quite close to, say, the projector screen, the maxima would be quite close together. But then if I walked back to the other end of the classroom and then pointed it at the projector screen, then the maxima would be further away from each other. The other thing we can do is increase the wavelength of the light actually going into the grating. That also increases the distance between the maxima. Now, you should know roughly the different wavelengths of different colours. Red and violet, if you can remember those two, then you're off to a good start. Red is roughly 700 nanometers and violet is roughly 400 nanometers. So please just remember that it does come into quite a lot of things. Okay, so that would be what our experiment roughly looked like in the class. Okay, we would shine laser light through a grating, okay, and we'd see these points of maxima or points of constructive interference on a screen. This is our formula that we need to know to do with interference using a grating. It's m multiplied by lambda is equal to d sine theta. M being the order of maximum. Now the order of maximum is exactly the same as how it was in path difference. You have your 0 order maximum, your first order maximum, your second order maximum, 0 order maximum, first order maximum, second order maximum, third order, fourth order, etc. You don't deal with minimas in gratings, so don't worry about that. It's just orders of maximum. So for this one, m would be 1, for this one, m would be 2, for this one, m would be 2, for that one, m would be 1. Lambda is just wavelength as usual. D is the separation of the slits. I will talk a little bit more about that when we look at the worked example very shortly. And theta is just the angle from the 0th order maximum. So here, see if we just kind of imagine a straight line going from our grating to the 0 order maximum. It's the angle within from the 0 order maximum to the second order maximum in this case. Okay, so it's the angle in here. Right, so worked example, a diffraction grating with 500 lines per millimeter is used with a monochromatic light source to produce an interference pattern. The first order fringe, okay, I've used that word because they sometimes use that. The first order maximum, the first order fringe means the same thing, is obtained at an angle of 25 degrees. Calculate the wavelength of the light. So first things first, we write down everything we know. I'll come back to this in a second. M is equal to 1 because it's the first order fringe. Theta is 25 because it's obtained at an angle of 25 degrees. Just remember that the angle is always between the 0 order maximum, is always between the middle and the order maximum. It's really important, and we're trying to work out wavelength. Now, D is the separation of the slits. Now, it says that you have 500 lines per millimeter. What D is, it's the distance between each slit. So what you need to do is actually take this and work out what the distance would be between each slit if you have 500 slits per millimeter. Okay, so you take 1 millimeter, which is 1 times 10 to the negative 3, and you divide it by 500. You divide it by 500, and that will give you the distance between each slit. Okay, so if it was 100 lines per millimeter, for example, you'd take a millimeter and you'd divide it by 100. If it was 1,000 lines per millimeter, you'd take a millimeter, you'd divide it by 1,000. Okay, that's something that people get wrong quite often. So just write down your formula. This one's nice and easy because m is just 1, so it just cancels out. So you get the wavelength to be 8.45 times 10 to the negative 7 meters. There is a way of working out if you are really wrong for these questions, because if you're talking about visible light, you will be looking for something in this region, like 8 point something times 10 to the negative 7, or 1 point something times 10 to the negative 7. You're looking for something in the nanometer area. So if the question says like green light is used for this experiment and you get a wavelength of like 5 meters, you know that that's wrong. Okay. Right, so I said I'd come back to this. This is just to do with how the spectra are produced and the differences between the spectra that's produced using diffraction gratings and the spectra that is produced using a prism. Okay, quite a common question in exams is they'll ask you for the difference between the spectra produced using diffraction grating and the spectra produced using prisms. Okay, so when light is passed through a diffraction grating, so white light is passed through a diffraction grating, central maximum is white, or the zero order maximum is white. Okay, but the other maxima are spectra, so there's more than one spectrum. Okay, now this is the opposite of what happens in a prism. Okay, red is deviated the most and violet is deviated the least. So it's violet first, then red, violet first, then red, and then the second order maximum would be violet here, then red there. Okay, and spectra are less intense when using a diffraction grating than they are using a prism. And then using a prism, only one spectrum is produced. Okay, so different from using diffraction grating. Red is deviated the least, then violet is deviated the most, and the image is bright. Okay, so those are just some differences between using a diffraction grating and using a spectrum. Right, that's it. Okay, using a diffraction grating to produce an interference pattern. Okay, I'll set you some questions, and obviously if you have any questions, please just let me know. Okay.